Hi, I'm Hyunjin Kim from Yonsei University, Korea. I'm going to present our paper titled Duplo Lifting Redundant Memory Accesses of Deep Neural Networks for GPU Tensor Cores. Our presentation is organized as follows. First, introduction. Then we describe the background and motivation on this paper. After that, we show details on Duplo architecture. And lastly, we demonstrate the evaluation results and wrap up the presentation. As the deep neural networks are becoming deeper and wider, GPUs serve as de facto hardware for DNNs due to its massive parallel computing power. Recent NVIDIA GPUs demonstrate this trend by incorporating tensor cores, which is specialized to DNN calculation and offer even greater operational intensity. Convolution is one of the fundamental operations in various classes of DNNs, such as image classification, generative network, and object detection. For instance, ResNet, GAN, and YOLO spend more than 99% of runtime on executing convolutions. Therefore, accelerating convolutions is essential to speed up DNNs. Let's move on to background and motivation. Convolution in DNN is performed as inner product between input data and convolution filter. Here, we use simple 4x4 input and 3x3 filter as an example. Starting from upper left corner, filter strides from left to right and repeats the process in the subsequent row until it reaches the end. This process is naive representation of mathematical expression. Therefore, we call it as direct convolution. In a program code, direct convolution forms deeply nested loops across multidimensional data. Lowering the convolution transforms the deeply nested loops into matrix multiplication. Each overlapping region of convolution filter is flattened into workspace. Once the input is flattened, we can calculate the convolution as matrix multiplication. Matrix multiplication can be rapidly calculated using GEM library, and we refer to it as GEM-based convolution. GPUs can better exploit a large degree of thread-level parallelism with this GEM-based convolution. Therefore, GEM-based convolution is the general choice of convolution algorithm for GPUs. However, lowering creates multiple duplicate copies of input data. As you can see in the workspace, it is filled with a number of duplicate data located in different positions of workspace. As a result, redundant memory accesses are generated to load the replicates of the same data from different memory addresses. Then what is the reason for this data duplication? Striding of a filter creates a grid pattern of data duplication. Each row of input is lowered and forms a grid tile called patch. Red dotted box shows a patch, and patches with the same color holds exactly the same data values. Horizontal striding of filter replicates data within a patch, and vertical striding replicates data across patches. And we found an opportunity to remove the redundancies, exploiting the duplication pattern. We propose duplication detection mechanism based on the observation of duplication pattern. The workspace can be conceived as multidimensional tensor, but usually the workspace data are stored as single dimension in DRAM. Therefore, to exploit the two-dimensional duplication pattern, we first calculate the row and column IDs of workspace elements. Then we calculate the patch IDs. Patches with the same IDs hold the identical values due to vertical striding of convolution filter. As the same patches are located in diagonal direction, patch IDs are also mapped diagonally. Finally, we calculate unique element IDs based on the patch IDs. Since horizontal stride replicates data within a patch, we use patch IDs as a starting point of duplication pattern inside patch. The resulting element IDs correspond to the indices of unexpanded input data. For example, we expanded 4x4 input into 4x9 workspace. Calculated element IDs are mapped into the values between 0 and 15, and each corresponds to 16 input data. Through this detection mechanism, duplicate data are uniquely identifiable based on convolution parameters and data dimensions. Tensor cores conduct gem operation on 16 by 16 tile, which can be written as D equals A times B plus C. Workspace and filter are mapped to A and B matrices respectively, and output is accumulated into D matrix. Here we only showed single batch, single channel, and unistride example for simplicity. But in fact, our detection mechanism can be also applied to more general cases such as multi-batch, multi-channel, and non-unistride convolutions. For multi-dimensional inputs, data belong to different channels and batches are appended to the direction illustrated in the figure. For more details, please refer to the paper. Next is details on Duplo architecture. Duplo architecture appends a small load history buffer to IDST unit to trace the history of workspace data and their locations in register file. When the duplication is found in LHB, a warp register is renamed as the one containing the identical values instead of issuing another memory request to fetch the duplicate copy of data. Duplo detection unit consists of two components, ID generator and load history buffer. ID generator calculates the IDs to distinguish the unique workspace data. Here, a tensor core load instruction of workspace data is issued. ID generator calculates the element ID using the detection mechanism and obtained element ID 2. Then Duplo looks up the LHB if the identical data were already loaded. We found an entry with matching tag 2, and it holds the physical register ID P2. Instead of fetching redundant data from memory, Duplo renames the warp register with the one recorded in the LHB. We already know that previously loaded data are stored in physical register P2. Therefore, we simply rename the destination register to P2. In this way, Duplo can avoid duplicate memory requests and handle it as a simple register renaming. When there's no matching entry found in LHB, data is fetched from conventional way from memory hierarchy. Lastly, we discuss the evaluation results. We evaluated the Duplo architecture on GPGPU shim with Tensor Core model configured as Titan V GPU. GPUs are known to hide memory latencies well, but Duplo is able to turn the elimination of tensor core load instructions into performance improvements. For example, The Oracle case with infinite size at HB shows 26% speed up on average. Where does the performance improvement come from? It is due to the aggressive load elimination capability of Duplo. Duplo removes up to 76% of redundant tensor core load instructions. About 3/4 of long latency memory loads turn into simpler register renaming. This result shows unhidden memory latencies have non-trivial impact on GPU performance. With this aggressive load elimination, Duplo achieves 26% performance improvements and 34% energy saving on average. Duplo replaces redundant memory requests with register renaming. By eliminating duplicate memory requests, Duplo saves DRAM traffic by 27% and turns them into in-SM register renaming. Also, the amount of data services by L1 and L2 cache decreased by 28% and 19%. Both forward propagation and backward propagation conducts convolution operation. Therefore, Duplo can be applied to both inference and training. We measure the network level performance of Duplo on 3 DNNs. As a result, Duplo reduces the inference time by 23% and training time by 8% on average. Since backward propagation incurs non-convolutional operations such as loss propagation, it shows less performance improvement than inference. Lastly, conclusion. In conclusion, Duplo saves a good portion of off-chip DRAM transactions and cache accesses, and turns them into in-SM register renaming. With aggressive elimination of tensor core load instructions, Duplo achieves 26% performance improvement and 34% energy saving on average. Thank you for listening. If you have any questions, please contact the email below. Thank you.